Hello all, and welcome to your last lesson and your last assignment for the first semester. So I know that we had a little bit of review on Monday, but if you are concerned about anything about the end of the semester, you want to ask questions, shoot me an email, set up a Zoom appointment. You are not going to have a quiz at the end of this week because I want to make sure that you have time to get everything in, turn everything in. You're also going to have a very short week next week, so it just makes sense to have one cumulative quiz at the end of week 22 on January 22nd. Again, if you have questions about anything, please get them to me as soon as possible because Thursday is the last day to get those things in. So we're going to talk today about what's called Euler's method, not Euler's method. I know I can see how it's spelled. It is pronounced Euler. So get yourself ready, and this is definitely one you want a calculator for. So if you don't have your graphing calculator with you right now, pause the video, go get it, and then come on back, okay? So here we're going to look at Euler's method from 9.3. You've got a couple of dispersed problems. And what Euler's method is a way to approximate a curve similar to a tangent line, but being much more accurate. So basically what we are doing is in comparison. So if I'm using a tangent line to approximate here, the single tangent line, we start at the point N, and then we can say, all right, well, a tangent line would approximate this next bit. And in this case, it's off by that much. That's the error on the approximation. Now, what Euler's method lets us do is that if we're looking down here, is that what we're going to do is use a tangent, I want to use a tangent line approximation to get all the way over here. Because if I just used a tangent line approximation, my error would be like this. That's not going to be super helpful. But what we can do is use little tangent lines and following the curve as we go, and you'll notice that, okay, well, now we only have an error this big. So each of these tangent lines is tangent to the curve at the points there above, like so, and then starting from where the last tangent line leads off. And that's how we calculate them. So let's just start with a quick review of how to approximate with just a regular tangent line like this. So approximate y equals 1, given y prime is equal to x plus y, and y at 0 is equal to 1. So basically, if we're looking at this drawing here, which is not the same, doesn't match the problem there, but let's help illustrate it, is that we're given this original point 0, 1. We want to approximate what's happening here by using the estimate here, which is 1, and we'll find the answer there. So the way that we want to do this is we want to start by writing the tangent line. And I will always use point slope form, which is y minus y naught equals m times x minus x naught. Now we're given our x and y here from the point, right? This is the point given. And slope is y prime. So here we've got y minus 1 is equal to x plus y at the point x minus 0. Since we know this is also 0 and this is also 1, we get y minus 1 is equal to x. Now, that's our tangent line. What we want to approximate is we're trying to find the y value here. So this is what we want to solve for, and we're given then that x is equal to 1. So y minus 1 is equal to 1. Add 1 to both sides. Y is then equal to 2. So what this tells us is that y at x equals 1 is approximately equal to 2. Off by this little error here. Now, what Euler's method is doing this same thing, but a bunch of times. In this case, it's illustrated as 4 steps, but just like with Riemann sums, the more intervals that you go over, the more accurate you are, but also the harder it is to do by hand, which is why I told everyone to grab a calculator. So, rather than spend a ton of time explaining this proof through, I'm going to talk through the formula really quick, and then we're going to work from there. So it's starts at the point slope that we just did, which is y minus y naught is equal to the derivative, which is the slope of x minus x naught. Since we're trying to find the next y value, we can solve for this, right? That's our y value that we're interested in, and we're plugging in our x values. And solve for that, you end up with y is equal to the first y value plus the slope times the difference of the next x values. And you can do this all the way through. Now, the difference of the x values is this distance here. So if this is our x0, our x1, x2, and just like with Riemann sums, these tend to be the same. And this is called h. For interval size, I can't tell you. It's one of those weird things that we've just all decided that it's h. And that's that constant difference here. And so the formula you'll generally see is that the next y value is equal to the previous y value plus h, which is that interval step size, times the previous derivative. So I'm going to walk through this step using the same problem. We're just going to use Euler's method with a step size of 0.5. So that just means that h is equal to 0.5. It would be the same as saying in 4 steps or in 4 subintervals. In anything like that would mean the same thing. Now, the way that I like to start Euler's methods problems is that I make a t-chart where I have my x values that I start at, and then I have my x value I end at, which in this case we go from 0 to 1. I know what my step size is in this case, so 0.25, the next is 0.5, the next is 0.75. Just fill them in with whatever you need to. Now your y values, we know what the first one is, but the next one is the one that we're not so sure of. But we're going to use that formula, which says use the old y value plus h times the derivative of that old point that you had before. So in this case, what I'm going to say is that the next y value is equal to the old one, so 1, plus the step size, 0.25, and then f prime, we're just going to use the derivative given to us here, which is x plus y. This is also coming from the step above. It's really important that you are using the previous information. So x, 0 plus 1. And this is why it's nice to have a calculator, so that you're not doing this by hand. This one isn't too bad. You end up with the next y value is 1.25. And now you're going to repeat the same thing again, except for you're going to use this new information. You're going to use that as your new y value, so 1.25 plus h, 0.25, plus the derivative, which is x, 0.25, plus 1.25 for your y value. And remember that this differential is changing. Like, I could have 2x here, I could have y squared. This is the part that's specific to the problem. And again, why you want your calculator here. So this gives us 1.625. Plug that in for the next step. You end up with 1.625 plus 0.25 plus the x value and the y value, because that's the differential that we're dealing with here. And typing your calculator rounded to places, going to keep going. Just keep using it in your calculator. Use the answer key. So you're like, I don't want to type all that out. So that is your second, and then on the negative, it just plugs in the last result. plus 0.25 plus 0.75, and then you can just use the answer key again on your calculator. Make sure you're putting in your parentheses there. And you end up with the final answer, which you do want to round to 3 decimal places as standard, 2.883. So you can see here that this is going to be a more accurate than 2, but they are reasonably close. So whenever you're asked to approximate something in multiple ways, which is a very common thing on the AP, just make sure that you're actually getting numbers that are reasonably close. Because if you have one that's super different, that's probably a sign that you didn't do that problem right. All right, let me know if you have any questions about Euler's methods or differential equations or anything from semester 1, and I look forward to talking to you after our long weekend, if not.